Hey everybody, it's March 5th, 2021. We are just cruising on through this school year. Today I have had my first dose of the Pfizer coronavirus COVID-19 vaccine. So let the record show that I'm feeling okay. So when you have a chance, you definitely should get it. So let's do some APOD and then we're going to talk about how stars make elements. And that will end our week here. Okay, so this is a very cool APOD picture. If you are a Sony PlayStation user, you may have heard of the game Big Little Planet, and uh, in that the gameplay, all the planets were really tiny and the characters were really giant, and it's become a tradition, maybe not tradition, but its own sort of subgenre of photography to try and mimic Little Big Planet. And this is supposed to be that. They actually refer to Mars in the description. I'm not quite sure why. I was kind of hoping there might be some animals, but even though there are no animals, they did something very cool. They've annotated this. So look, there's Orion, and since this is in Chile, where one of these, major observatories is located, you can actually see one of the domes there. This is Orion upside down from the perspective of a, northern hemisphere person like me. So there's the Pleiades, there's a large and small Magellanic clouds, there's the bright star Canopus, which I've actually seen in our sky. There's the bright star Sirius, and you can see all the nearby locations for the photographer. So you get this sort of all, you know, sky view. Oh, there's Mars. And you can even see this thing called the zodiacal light, this kind of fuzzy bit here, which is the dust from the solar system backlit by the sun. It actually shows up in really dark skies. I've actually only seen it one time. So I just thought that was a pretty cool picture. Um, and kind of a neat little way to end Friday. So if you ever get a chance to play Big Little Planet, or maybe you already have, do that. All right, so let's do this. We're almost done with these. I want to talk about how stars make elements. So we've got 81 stable elements from the periodic table, and that we can find here on Earth, and there are 10 radioactive elements that we can get here on Earth. Almost all of those from mining, but not all of them. How did they get here? Now, there are more elements, of course, on the periodic table, but they don't last very long. They're not very stable. And when we have encountered them or manufactured them, they fall apart pretty easily. So here is a kind of a familiar, at least to astronomy nerds like me, graph of the abundances of the elements in the universe. And any model that explains how the elements in the universe are made, the modeling better match what we actually see. So we're going to talk about that towards the end here. So a couple of points. Look at hydrogen being at the top there. Thanks to Cecilia Payne-Gaposchkin, we recognize that hydrogen is the most abundant element in the universe. And now we have really good data to back that up. But you can see there's a lot of hydrogen, there's a lot of helium, and it sort of follows this curve here. There's carbon and oxygen, neon. Notice iron up here at the top of that curve. But I want to mention these three: boron, lithium, and beryllium. The mechanisms by which stars make elements skip over these three. Now they're not always. Some obviously there's some boron, lithium, and beryllium in the universe, and the processes that make elements in stars also make these three. But I'm going to tell you why in a minute. It's pretty common for processes that make elements heavier than hydrogen and helium to not do these three all that commonly. So there's a lot of carbon, a lot of nitrogen, a lot of oxygen. You can see neon is there, magnesium. And I want to mention iron because when big stars, more massive than the sun, when they make elements through nuclear fusion, this is the end point before they supernova and produce either a neutron star or a black hole. And elements that are produced during a supernova or during kilonova events, they'll decay by different nuclear processes until the number of protons matches that of iron. So you fusion gets you towards iron from kind of the left side of this graph. Fission gets you to iron from the right side of this graph. So we've kind of discussed that already. I just wanted to sort of remind you of that. So Why is it that we kind of skip over the boron, lithium, and beryllium? And it has to do with the fact that stars like the sun, um, I want to touch on one other thing. Hydrogen is the result of a proton and an electron being as close together electrically as they can be. So, as the universe was cooling after the Big Bang happened and several different stages went on, and I will go into that later, I promise, hydrogen was the result of protons and electrons finding one another. So, the hydrogen in the universe did not come from stars, and even a lot of helium was produced during this period when the universe was in this very energetic, very chaotic state. And I'll touch on that later. But anything heavier than hydrogen and helium, astronomers kind of lump, which is everything, astronomers lump into the category of quote unquote metals. Now, it's not what a chemist would think of as the metals that have particular properties and especially uh, conductivity, but that's what astronomers do. So we refer to things that stars make and kilanovae make and supernovae make. We refer to them as metals, and there's not really good reason for it, but I just wanted to make sure to say that. So the deal is stars like the sun make a whole lot of helium as they age. You end up with what's known as a helium-4, two protons, two neutrons. This is the most common isotope of helium. And as stars more massive than the sun have their second life as they become red giants and they pass the uh, uh, point of fusing helium into heavier and heavier elements, you'll note. So this is making their three heliums here, triple helium process or triple alpha process, making a carbon 12. The 12 in this case represents the total number of nucleons. So that's protons and neutrons. Same with the helium 4. This process means that there will likely be elements that have not two protons, not even four, honestly, but often six. So carbon turns out to be, if you're looking at this, there's, one more, two more, three more, and the carbon is wait, did I count that right? One and then two and then three and then four and then five and then up to six. So helium has two, then we've added one for lithium, another one for beryllium, one more for boron, and then carbon turns out to be basically the most common path for a star like the sun to have its kind of second life when it's on the horizontal branch and it's fusing helium at that more than 100 million Kelvin mark. You're fusing into heavier and heavier things. So carbon turns out to be a really common element. So the fact that carbon is an easy chemical pathway for life to make structures and build upon. There's a lot of it in the universe, so it's not that strange that its chemical convenience for life is also the reason it's so common, I would say, is that it's in life, I mean, is that stars make so much of it. So I want to talk about stellar nucleosynthesis in that context. There's Big Bang fusion, which I promise we'll get to. That's hydrogen, helium, a little bit of lithium, but notice that there are all these other pathways for making stars. There's cosmic rays, which are particles that were emitted by really massive explosions, and they'll occasionally run into an existing massive atom and force it to split apart, hence the word fission. And almost all the beryllium is made that way, almost all the boron. So it's actually a more common pathway for making them. But look at lithium also has this big chunk here. Stars like the sun, there's a process called the S process, the slow absorption of neutrons. Now, an absorption, whoa, that was a weird phrase. Neutrons being absorbed, that's not really a slow process, but if it doesn't happen all that often, we call it slow neutron capture because there's also rapid neutron capture, and that's where you would have exploding massive stars, merging neutron stars, and exploding white dwarf stars. So, and you'll notice there's also a category here for these like americium and berkelium, Kellium, is that right? Californium, these guys that are made by human beings. But the purple, the green, the yellow, and the white, they represent ways in which neutrons are forced into the nucleus of existing atoms and pathways to make all these other elements. I would mention that there are a couple of weird ones here, like uh, technetium here at 43 has an interesting story, and that there'd be a really interesting video just on how the elements got their names and how we use them in life and stuff like that. But you'll see that a lot of the ones are purple here. So we now know that one of the most common pathways for really sort of big atoms to be produced, especially all these lanthanides here, the lanthanide and actinides, this particular period that we have there, these two, it's actually most common for them to be made by merging neutron stars. And then you can see the purple spread all throughout this section here. So, stars like the sun go through the capture of neutrons through the slow process. But when neutron stars merge, that is a rapid neutron capture process. The same thing can happen with exploding white dwarf stars, and exploding massive stars. They can make lots and lots of elements through the merger of atoms while they're actually exploding. Okay, so I mentioned that alpha particles make a lot of carbon. If you add two carbons together, you get magnesium 24. But if a carbon and a helium add together, you get oxygen. So you'll notice that it's often either doubling of the elements or an element, or I guess, nucleus, doubling of the nuclei, or a nucleus that is bombarded with helium particles and emerges, it fuses with one of them. So those are the two most common pathways in a star for this act. Like the nitty gritty here is like, how do they merge? You either double the nuclei or the nucleus absorbs a helium atom. And of course, there's the neutron capture thing, which I don't want to skip. But thinking about the role that helium plays, so much of the periodic table, especially having to do with things that end in, um, life chemistry, is the result of helium atoms merging with other things. So you can see there's a pathway here for making, well, I just covered it up with my mouse. Uh, that's annoying. Let's hit exit so I can see it. There it is. Silicon 28, sulfur 32, argon 36, calcium 40. Maybe I'll just move this up some instead of being annoying. Sorry, y'all. Real-time editing. And it's like really being in class, right? So that way I can go back into presentation mode. There we go. Well, still pretty annoying. Calcium 40, titanium 44, chromium 48, iron 32, and you finally ended something called nickel 56. Now, you don't need to know this pathway, but I'm just showing you one of the ways that you keep adding helium nuclei during processes that are going on in an older star, and you end up with this. So you can see here this silicon 28 atom gets hit by maybe a cosmic ray or some other high energy particle, and it splits into a whole bunch of these helium atoms, and those helium atoms are then going to merge with other existing nuclei. So this is a pathway to get all the way up to nickel 56, which, by the way, it is likely, well, remember, iron and nickel are the two most common elements in the center of the Earth, so that this is the pathway that we make those things. So this is known as the alpha particle chain, and nickel 56 is the end, but it's pretty common for it to still fall apart and become an iron 56 atom, and or I guess nucleus. So this is the sort of end of the alpha particle chain. But of course, and I'm not going to get into a lot of the details because this is not a nuclear physics class, but we really do need to remember that it's not just the doubling of atoms of nuclei. It's not just that there's a bunch of helium atoms to smash them together, but there's also a bunch of processes that cause a neutron to end up inside a nucleus. And what you need to know about that is by adding another neutron, the neutron will often decay and leave behind a proton in the nucleus. So capturing a neutron means it will convert itself into a proton. And when it does, you just made the element number go up. So the S process happens in stars like the sun. Well, as stars age, neutrons kind of running into atoms that are already there. So that's called the S process. But during a kilonova and a supernova, that's what we call the R process. It happens rapidly. So I wanted to make sure to spend just a few minutes discussing how important this process was to research that I got to do. So I was lucky enough to be on a team of four astronomy teachers that tried to look for one of the elements that is created by the R process in stars, well, especially in kilonova explosions or neutron star mergers, if you want to call them that, europium. And astrochemists, chemistry people, physics people, and astronomers were all very curious how it is that europium and elements like europium make their way into stars. And there is a known number of stars that have R process uh, europium if the metallicity is really, really low, meaning that they have a just really shortage of the heavier elements. And of course, ones like the sun and stars that are in the Milky Way, we already know how they get theirs. There is this gap, though. There are these stars that are kind of missing some elements, but not that many. And this kind of blank area, not the ones that have rare that don't have a lot, not the ones that have a lot, but kind of the ones in the middle. And so I got to help answer the question of, well, where are these sort of like a little bit of metallicity stars, and how does europium get there? So you can see the here are five, one, two, three, four, five target stars. You can see their weird names right there. And the reason we were looking for europium as a way to look for R process elements is europium's spectral signature happens to have an absorption feature, a little dip, that's very close to one of the lines of nickel. This is neutral nickel. So stars that are a little bit metal, a little bit metal, and stars that have this europium line, they're kind of in the same category. So we can use nickel in the spectrum as like a fingerprint since it's so close to the one we're actually looking for. So you can see here we've marked the nickel line, which stands out really, really clearly in each of the stars. And in the europium line, look, it's missing in this one, this TYC 5701 0019-1. There isn't really any bump, any dip there from the europium for that star, but all of the other ones had a dip. So I kind of mentioned this pathway already of the atoms becoming other things, but I wanted to just vaguely tell you that when europium is made and other things like it is a very complicated process. It is not as straightforward as what I just described with the absorbing neutrons or doubling the nucleus, that kind of thing. It's even weirder than that. It's even harder than that. There's a lot more sort of quantum physics and atomic physics that you got to do to figure out the likelihood for europium to be made. And so, what I was trying to do, along with my teacher cohort friends, is we had like 50 stars we were taking spectra of, and then we had to go through them all and see which ones had the signature for europium and which ones didn't, and submit that data to our scientist. And he was like, nice. So that was cool. I just want to just I've said so many different things. I wanted to make sure to kind of put this together. So and there's obviously a lot more to the story, but these are the three things I would want you to know. How do we make heavy elements? Well, you can double the atoms. You can make them absorb a alpha particle, which is a helium-4 nucleus, so two protons at a time, or you can make them absorb a neutron, which then decays away into a proton. So here, whatever the atom is, you literally double the number of protons. Here, you just add two protons. Here, you just add one. And these three processes sort of fill out the periodic table. And what I said at the beginning of this little talk here was any model that explains how atoms are being made inside stars needs to match what we actually see. And this is exactly what we find. Astrochemistry is confirming what particle physics and atomic physics says should be true. So what we're finding by looking at stars and nebulae and dust grains from space and looking at the atomic abundances, it actually matches what the models for atomic physics actually predicts. So that's a really good sign that we're on the right track. But this is still an unknown thing. Like this stuff about europium, like I did this just 2 years ago. So it is still unanswered how some of the elements on the periodic table get to where they get. And, each little bit that we chip away from the, ignorance block is helping in answering that question. Okay, that's good enough, y'all. I hope you stuck with me through this, and I hope that you end up having a great weekend on this Friday, March 5th, the day of my vaccination. Bye.